grab pulsar scintillometry results, and then J.P. McQuark is going to talk about birefringence and pulsar scintillation. So first of all, Barney Rickett for 15 minutes plus 5 minutes of discussion.
Okay, so my title has changed, my topic has changed, so I apologize for pulling a fast one. I introduced some of what I would have said in this talk into the tail end of my introductory talk, in which I was concerned with the frequency dependence of the arc phenomenon somewhat, and trying to characterize that and use that as a way of constraining the models. So the models that are out there, well, they're pretty skimpy. We've got scattering and refraction. Those are two aspects. And scattering involves a turbulent structure which is inhomogeneous. It's small to get this localized phenomenon, but it's inhomogeneous internally, and that scatters the waves. Or it could be a concentration of plasma, well, absent plasma even, which will refract the waves. And because it's plasma, the refraction goes, it's a diverging refraction in a plasma. If you've got a concentration of plasma, that creates a diverging structure. So that's a bit like scattering in a way. It deflects the waves. It doesn't converge them. Though, of course, just to sort of do an end run on the possibility, a converging system, if you're close to the lens, you're in a converging region. But if you go beyond the focal point, it's diverging again. So it can be either way. And I'm going to drag you through some very basic algebra. Refractive index in a plasma, as you know, depends on, it's less than 1, and depends on the electron density in particles per cc. And it's got this number in here, 10 to the minus 10. If you take a wave through a sphere, say, with a radius a, and you compute roughly the plasma phase, that's the part due to the NP as the radius, that's a typical depth, 2 pi over lambda, and this NP. That's the phase change. The angle of refraction typically would be then given by the phase gradient. So if you put those two things together and you make the very crude assumption that the phase gradient is roughly the phase deviation divided by A. That's the size of the task. That gives you that the angle of deviation equals the refractive index deviation. This is pretty small. If you take 10 milliarc-second deviation, for example, from the various lensing, from the various arc measurements, deviations in the order of 1 to 10 milliarc-seconds have been estimated. So, and this is typically at a wavelength near 1 meter, so that you turn the this into an angle, and then you ask what is the electron density. It comes out to be 100 particles per cc. That's embarrassing. It's way beyond equipartition of pressure in the ISM. Even if you go down to 1 milliarc-second, you're left with 10. The line of sight average electron density from pulsar DMs is about 0.02, 0.03 perhaps. And this is something weird. Well, I mean, that's why we're here. So what do we do? Well, a theoretician says, all right, well, you've got to stack up the depth that the waves have gone through. So we flatten the sphere and we have grazing incidence. And so we have an axial ratio here, which cranks up the phase in this direction. It doesn't change the gradient factor, and you can get a larger angle, or the electron density you imply is reduced by this axial ratio factor. And that's where we've been headed all this time. And I took this sort of grazing reflection, grazing incidence to the limit. So now let this just be an ideal interface between a plasma density here and a lower one there. So the refractive index here decreases at this point here. You can, in principle, get total internal reflection. So the conditions for that, I mean, the Snell's law can be written n1 cos alpha 1 is n2 cos alpha 2, and that corresponds in small angles to this relationship between the two angles and the change in refractive index. This is not NECC, this is refractive index. This one is close to 1, and 1 minus a tiny bit. So if we have this case of plasma density here, then you get a refractive index, a critical angle, which is where this condition breaks down. Sorry, where this condition breaks down. We get cos alpha c is equal to the ratio of the two, and you push it through. It says the critical angle is a square root of 2 delta n. That, again, that's the refractive index. Now, this is delta n is a number less than 1. When you take a square of a number less than 1, it gets bigger, right? The square root of 0.01 is 0.1. So this is a larger angle. So if you can associate the process with reflection like this, you don't need such large densities. And the numbers are absurd. And I've hesitated to put this out in public for about a year now. And if you can point out where I've gone wrong, I'd be really grateful, because it seems weird. So if we identify an observed 10 milliarc seconds with twice the angle of incidence, that's a reflected wave, we need the alpha 1 to be less than the critical angle. So 2 alpha 1 measured, and so that means that the critical angle has to be greater than this in radians. Delta n alpha c squared has got to be greater than that tiny number. Turn that into a difference in electron densities, and it says the difference in the electron densities has got to be greater than 10 to the minus 6. Well, that's nothing. 5 minutes. So you can play it the other way. If you put in 1 particle per cc, the critical angle is 6 arc seconds. These are large angles in the scintillation business.
But that means that your thing has to be aligned to its...
Yeah. Okay, so several things have been, it's got to be aligned. Good point. It's assumed to be a discontinuity, but in fact it could be like in an optical fiber. There's an increase in density. The ray will be turned around at the same condition, really, as for internal reflection. Take it further. Let the surface be curved. Then you don't need the special alignment that Martin is emphasizing. And it'll, again, the ray will get turned around on that condition. So this is reflection and refraction are not really different. This is a reflective view of refraction, I think. And here's the rippled sheet, which is popular in this part of the world. And you can get this reflective refractive reflection or reflective refraction, I don't know, from the top surface, the wave can go through if it's higher than the critical angle, and then it could get reflected from the underside. And I think this is very similar to what is being proposed by Dana, Simard, and Wei Li here. And I went as far as taking one of their, I don't know if you've read this. Oh, here it is. Here's a sheet of plasma, curved, of a certain thickness, and the ray goes through it, and you get a phase profile like this. And I put this into the simulation code that I've been running, a phase screen. But I had to round the corners a bit, because this is a discontinuity in slope. If the density is abruptly changing here, and I simply convolve the original with a little Gaussian to round off the edges, and that made the computation easier. And then I computed the magnification using geometrical optics. There's one here, and one here, and these are the regions where there's multiple ray paths and even caustics. And I put the same phase into the diffractive simulation, and this is what I got for the intensity. And the reason that this is so important is that the proposed thickness of the plasma sheet is about a couple of Fresnel units, Fresnel radii. So you really need to talk about diffraction. And so this is an illustration of, we've got to take into account the possibility that diffraction and interference are important. Evidently here, I've got three rays, three different magnifications. You can't just add the magnifications. They're interfering with each other. And the same here. And that's what causes these ripples. These are seen in many such things. Here it is versus frequency and space. Pretty boring, really. But I put that into the dynamic spectrum computation, and wow.
So Barney, just going back to the previous slide, it's versus frequency, but isn't that's a fairly narrow band?
This is 10 to the minus 4 in frequency, yeah. Yeah, tiny. I thought I'd gotten down to the... but then I put it into the dynamic spectrum computation, and this arc turned out. A forward arc. Now these are aliases. The frequency resolution in the computation wasn't high enough. So what I did was to take this one and do a difference in the frequency direction and plot the difference. That's the first difference in versus frequency. Now you can see this sort of fine scale structure. And I couldn't figure really what they were, but I think what they are, they're the interference between these multiple ray paths. And it is this structure, which is not quite resolved, which shows up in the secondary spectrum in this fashion here. And let me just end then with, I won't go through that, I've sort of said it. That is what causes the fine structure, low-level fine structure in the spectral domain. That is the angular spectrum computed along a long plane in which the intensity is, well, I guess it's varying like that from very low to ripply high. So this is taking the Fourier transform of the entire domain to get the angular spectrum. And here it is computed at 3 frequencies. And I'm at a bit of a loss how to interpret what the scaling is, how to characterize the width of that. And I took cuts at 10 dB, 20 dB, 40 dB. And I've got results of the scaling law between 2 and 5, depending on where I took the width. I really don't know. So my conclusions are here. We do need to take the wave optics analysis into consideration. But I think that the geometry is beginning to look more and more like Whaley's nice picture of the reflections from the Toronto skyline. Okay.
Okay, thank you very much. Okay, we have time for some questions. Yes, Robert.
Yeah, so the folded mountain, do you look only at an overdense fold or also?
This is this was an overdense.
Repeat the question.
The question was, the folded sheet is an overdense plasma. So there's an increase in electron density in the sheet, not a, I haven't tried putting in a dip.
Is that something that would be easily supported by your simulation?
Oh, I should think so, yeah.
Okay, because
Yeah.
I think the general picture is, I think that's the one that's favored by the frequency scaling of theta.
But I mean, that's using the geometrical optics analysis. I think it needs to be re-examined using a more, I mean, that's what I'm trying to get into, the frequency dependence of these phenomena. I mean, I should point out, if you take the secondary spectrum here, or the secondary spectrum there, or here, or here, I haven't even done that experiment to see whether it varies across the screen.
Other questions? Yes, Chris.
What's the length of the structure along the line of sight?
It's about 10 or 100 times larger than its width. It's actually written down in the papers produced here, and I've just taken the results, and I haven't deduced the width or the length. I'm just taking a model which has been published and trying to look at it from a more detailed analysis. So it's very interesting to explore this. Can we constrain the width or depth? Could it be refraction in this form with no scattering? Because this is a smooth medium inside the sheet.
Whaley, last question.
It's certainly a fascinating picture that's very different from anything else that people have been discussing. I do think that there's a generic expectation of this, which is that at any given frequency, there will be a hard cutoff in scattering angle, right? Because you've got this go, and at least for a physical over there, let's say a limit where delta NE to be some number 1, let's say. Then there's a hard angle, and that angle goes as lambda squared.
Right.
From internal refractive laws. Because lambda squared part for the scaling in general is always a good thing. That's kind of what many things are known to scale as. But this hard cutoff, I think, is something which would be interesting to compare. I mean, this like what JP was saying, the harder you look, the further you find applets, and this kind of picture, at some point you will stop finding them. At some point there will be a hard edge.
I mean, and a related factor is that there's a problem in traditional scintillation analysis of the way the scatter broadening time scales with the radio wavelength. And people have been looking to find values greater than, is it 2.2 or 4? It's 4.4.
Yeah.
And they always find them down below 4, 3.8. That maps into a scaling slower than lambda squared for the angles. And could it be there are some reflective features in the medium whose deflections do not depend on angle, or on wavelengths rather, because they're below cutoff, or they're below the critical angle. So it opens a sort of ball of wax, can of worms.
Comment, we will have to move on. Thank you very much. Okay, and so doing better than that, but he
No,
will give us his full title.
It's actually, it's a little bit obvious because I had not really planned to talk about it, but over lunch I realized that, of course, not everybody goes to the 50 years of pulsars meeting. I assumed everyone had, or is at Toronto and therefore knows these things already. I just want to be absolutely sure because I actually didn't look at
HDMI.
Excellent.
All right. So, so as to talk about scintillation in a birefringent medium, and I just wanted to draw your attention to a couple of effects that may or may not be relevant in the interstellar medium, and their relevance or irrelevance will tell us something about the nature of the interstellar medium and the magnetic fields that thread it. So, the basic effect, if you want to fall asleep for the rest of the talk, is this: that if you take a piece of text, for example, and shine it through, or just look at it through some birefringent medium, you see two images of that piece of text. And that's because that piece of text, the light from it is unpolarized. But something like calcite has two refractive indices corresponding to the two natural modes, to the two just the two refractive indices that correspond to two polarizations in that particular crystal. And just as this calcite produces two images, so can the interstellar medium, except that the difference in refractive indices is much, much smaller and may or may not be relevant. So how does this happen in the interstellar medium? Well, in a cold plasma, which is what we assume the interstellar medium to be, to a very good approximation, you have two natural modes, and they correspond to right and left-hand circular polarization. So Barney was talking about the refractive index of the plasma just earlier in this session, and he was concentrating on this term here, this 1 minus x term, where x is this ratio of the square of the plasma frequency to the angular frequency of the radiation. So this extra birefringent term, which is smaller by this value y, which is the electron cyclotron frequency on the frequency of the radiation. This is the effect of the birefringence, and that's that effect that gives you Faraday rotation in the interstellar medium. And of course, as you can see, it's a very much smaller effect. But what happens if you try and incorporate it in the theory? Well, here in its glory is the wave equation projected onto the transverse plane, and we have some dielectric tensor that we get from plasma theory, and we can write that as some mean contribution and some fluctuating contribution, and we'll take the mean of the fluctuating contribution to be 0, and we'll carry that forward in the theory. So if we do that and specialize that to the conditions that apply for a cold plasma in the interstellar medium, you end up with two separate equations, one for what I've labelled U plus and U minus, and these correspond to the right and left-hand circular polarization. So I've decomposed the wave field, as I'm free to do, into the right and left-hand circular polarization, and I've now got terms that link these wave fields to the perturbations in the dielectric tensor, where I have these. I can write down what these things are just by. I can write down I plus plus and I minus plus and all of these things, and just using the definitions of the Stokes parameters, this is what these visibilities become in terms of my generalised second order moment of the wave field. With me so far?
Absolutely.
Great. Right. So I can then use my wave equation to get an equation that tells me how this particular thing propagates, and I solve it. And we won't worry about the solution all that much. I'll show you the solution in a moment, but we won't go through the mechanics of it. What is essential, though, is that we've been talking about the phase fluctuations up to this point and the power spectrum of the phase fluctuations, and we've been only taking the isotropic part of that response. Now, a function which in a normal non-birefringent medium would just look like this, now becomes all of this. So I have to worry about all of these effects due to correlations between the phase, between the isotropic phase and the anisotropic phase, and if they exist, and then the structure function of the Faraday rotation terms as well. And in fact, in this particular version of the structure function, I also have a contribution from the autocorrelation as well. So I have to carry that forward in all of the theory, and then that makes it just a little bit more complicated. So here, if I do all of that, are the visibilities in the 4 Stokes parameters. And they show some things that we're pretty much familiar with, right? So let's just pick on the total intensity. If I have no Faraday fluctuations, no Faraday phase fluctuations in that medium, then this dVV, which is the phase structure function of the rotation measure fluctuations, that's 0. So e to the minus 0 is 1, and then if I start off with no circular polarization, then this is 0. This is the correlation between the normal density perturbations and the Faraday phase fluctuations. And again, if I have no Faraday phase fluctuations, then this Koch term becomes 1. And that means that I just get, for example, my familiar result that the visibility in Stokes I goes like this thing here, which describes the normal effect of scatter broadening due to turbulence in the ISM. Now, if I let there be phase perturbations in the Faraday term, I get a couple of extra effects. First of all, I get mixing between Q and U, and that's just Faraday rotation. We all know that. It's all easy. The extra thing that I get here is that I have this dVV minus CVV. So if I forget about this phase structure term here, I just look at this. It tells me that I've got this e to the minus 2 CVV term. What's that? That's the variance in the Faraday phase. So it's saying that I depolarize Q and U by amount exponential to that Faraday phase. And that's just Faraday depolarization, which we also know and love. The interesting thing that's slightly new, but actually only from a formal point of view because the effect is too small to measure, is that if I start off with something which has no circular polarization, I can actually get a visibility in V that is non-zero. And the reason is due to this thing here. So you can see over here that if I start off with Stokes V is equal to 0, I can still get a non-zero contribution because I, of course, is going to be non-zero, as long as this term, this diV term, is non-zero. So this is only going to happen when the baseline between my two telescopes is non-zero. So I can, in principle, although I'd still get 0 circular polarization measured by a single dish. An interferometer might actually measure circular polarization in the visibility. The interpretation of that, and this was, by the way, identified in the early 1990s, and the interpretation of that is that the two scatter broadened images in the left and the right hand polarized wave fields are slightly different. There's a slightly different value for the diffractive scale for those two polarizations. It's very small. The effect is of order alpha, and therefore it's only of formal significance. It's not really measurable, I would say. But in principle, it exists. And that's the interpretation. So, now we have to ask, well, what about the variations in Stokes V and all of this business? And then you have to deal with this hideous quantity, the fourth order moment of the wave field, which is interesting enough when you're just doing it with the total intensity. But now you have to label all of these things according to their polarization. So we have 4 telescopes. We imagine 4 telescopes, and they're each measuring one sense or another of circular polarization. And so we write down an equation for the propagation of this fourth order moment. And if we do that, we get this hideous thing. But the reason I'm showing this is because it has an elegant symmetry. So if I look at, for example, Stokes I, you can see I have terms that correspond to the input variance in Stokes I, but I also have a term that depends upon the correlation between I and V, and v squared. And similarly down here, when I look at the propagation for v squared, I have things that depend upon the correlation of I and v squared. But if the circular polarization is initially 0, I remove those two terms, I still get something that corresponds to the input total intensity. And so the symmetry persists for Q and U, right? So for Q squared, I have a Q squared term, a QU, and a U squared term, and that pertains to all of these cross correlations. Just to show you how hideous it is, these are all of the terms that actually appear in those various equations, just for completeness. Thank you, Dan. Right, so what about these effects? Well, let's just pick on these effects and see what happens to the circular polarization when the input circular polarization is 0. So we have a term that corresponds to just a non-zero total intensity. If you expand it all out, you get something that looks like this. So if we were just talking about scintillation in a non-magnetized medium, I'd remove this line here, and this just gives me the normal effect of scintillation. But now I have 3 extra correction terms, and I can pick on each of those individually and look at what they give. And not to belabor the point, this one gives an effect that looks refractive in nature and changes the circular polarization by amount that corresponds to alpha being that ratio of the electron cyclotron frequency on omega times the refractive modulation index. So this is very small. The next term here is actually this effect due to the birefringence that I was talking about, that basically gives you separation of 2 images like you saw in that image of calcite, and I'll come back to in a second. And this in principle may be large. And then there's another term which in the regime of strong scattering is always small. So I think in the view of the time, I won't go on with that. You can actually do the same for the propagation of Q squared plus U squared. So although you see that Q and U average get depolarized, the interesting thing is that Q squared plus U squared doesn't get depolarized in the same way. It persists. Even if you have rotation measure fluctuations across the scattering disk, you don't depolarize P squared average. So this term here corresponds to the normal scintillation of the polarization. This one here corresponds to a slight removal of linear polarization due to the conversion of some of the total intensity into circular polarization. And then there's this term here, which is insignificant. And then you can look at the rotation measure fluctuations, their effect on Q squared and U squared. And the only point I want to make out here is that P squared average doesn't get depolarized by Rn fluctuations. So if you're able to resolve this within the diffractive timescale and bandwidth, you can still see the full polarization. This is the solution for weak fluctuations in the Rm. I won't go into it, but you can derive what the variations in the position angle are. And just to end on the high, this is the physical model for what happens to that circular polarization, this effect, the only effect that seems to be large. The idea is that you might have some gradient, or there's some variation in the rotation measure phase across the size of the scattering disk. And if that's the case, then as structure gets imprinted upon the wavefront by the scintillations, when they arrive at the observer, there's a slight lateral displacement due to this wedge that gives me a slight difference, instantaneous difference in the circular polarization. And that's what causes this. This is essentially shining radiation through a piece of calcite where the text is actually this structure that's imprinted on the ISM. So I think I'll end it there, except to say that you can actually build a model up out using the stationary phase approximation and get the same result as was proved formally. But and you can then use this Faraday wedge model that I just showed you a picture of to derive some condition for the production of circular polarization, if you're interested.
Okay, thank you very much. Okay, questions for JP? Yes.
The relation between the
I think the magnetic field, well, there'll be large-scale fluctuations in the magnetic field. I don't know much about how the magnetic field fluctuates on any of these scales, to be honest.
But I think you're talking about magnetic field that is fairly constant or any
Yeah.
next scale. I was talking about like topics. I think
Yeah.
in this vision we've got to be thinking about a basically constant over that scale.
So when I write down, for example, these DVV terms, these things that looks is the variance or the phase structure function in this in the Faraday phase, you can decompose that into bits that correspond. So, for example, you could just have a constant magnetic field threading through the medium, and you'd still get Faraday fluctuations, of course. And then you have to consider what the correlation between the electron density and the magnetic field is, and then what the fluctuations are in the magnetic field. Even if those two things are absent, you can still get this sort of effect. But it's far more interesting, of course, to consider what those fluctuations, what the relationship between the electron density and the magnetic field actually is.
Well, let's see if I get my picture of where this slide equation and weights, but if I can follow it simpler, what I can might be able to internalize, that if you have a Faraday wedge, which I think generically you have, if you have a constant magnetic field and some variable electron density, so a wedge, only one of those two has to vary. So the product of n times b
Yep.
has a spatial gradient. In which case, I would think in the absence of high-scale structure, I would just see the left and right image for an unpolarized source. I would now see a displaced position of my left and right images.
Yeah,
So the
precisely.
wedge causes a slight displacement, and now I see the left image slight, let's say a bank arc seconds to the right of my left image. That might be hard to measure in practice, but now we're going to add the scintillation in this grain. And now I think we're doing what Martin was just demonstrating, that you have two pulses coming from slightly different positions in the sky, perhaps one arriving, say, a millisecond earlier than the other. I mean, it's not arriving, the pulses arrive at the same time, but the apparent position, the whole thing is moving. So you actually would be looking, I think that's what, I don't think we're going to talk about it, but for instance, now, I think in practice, what this would say is that if you do the exact same exercise of looking at the two cross scintillation patterns, you may see a slight shift in the cross correlation of the scintillation pattern in left and right.
Yeah, you've essentially, you'll get some non-zero circular polarization if your shift projected onto the observer's plane
Yes.
is some fraction of the diffractive scale.
Exactly. So all you're doing is I think the two will shift a little bit in time, and that's what you might see. And the way you go after it is after what Martin just showed, just correlate those, cross-correlate those two and see if there's a lag in time. And it could be sensitive, not actually linear. It would be linear, exactly. So it would be just like the cloud offset in this case you have small one. But if you have a velocity bullseye, you can easily imagine going down to about 1,000 sensitivity by such a. So I think in terms of language, you're not talking about, you are not? You're not. Okay. Then basically just by taking the cross-spectrum, dynamic cross-spectrum between I and B.
Yeah. Or you could just resolve, well, you could just resolve it into the right and left-hand circulars and just do that. Just cross-correlate those.
On a cautionary practical note, I would assume that any kind of polarization, impurity, and imperfection in your instrument would wreak havoc with some of these effects.
Well, it's interesting. With 0834, the observations there, we thought, well, gee, what on earth can create these structures? Maybe there's some magnetic field that's confining it, and can we see this effect? So the idea was there. You don't know, you don't have a very good calibration, but this effect should be flitting about on the timescale and the bandwidth of diffractive scintillation. So you make a secondary spectrum of it. And there, if you see it non-zero delays and Doppler, an effect in some power in the circular polarization, then you can be fairly sure that it's being generated by this effect, and you can remove a lot of the instrumental effects, which is the same as Whaley's saying cross-correlating the the dynamics